Okay, I'm going to begin section 2.6 now. We're going to talk about limits at infinity. Now in section 2.2, at the end of that section, we talked about infinite limits. An infinite limit is different from a limit at infinity. Okay, and I'll talk more about that here once we talk about limits at infinity. In this section, we're going to discuss the end behavior of a function on an infinite interval. So let's take a look at an example here. Suppose that we have the function f of x equal 3x squared over x squared plus 1. Now this is a rational function, okay, so I'd have to be aware of any asymptotes that would be on the graph. There would be no vertical asymptotes on this graph because the domain of f of x would be all real numbers. There's no number that's going to return 0 in the denominator there for us. Y equal 3 would be a horizontal asymptote. Since the degree of the top is the same as the degree of the bottom, I can just compare the leading coefficients there. 3 over 1 is 3, so y equal 3 would be a horizontal asymptote. And I've plotted a couple of points, like if x is 0, 0 over 1 is 0, so here's 0, 0 on the graph. If x is 1, 3 over 2 would be 3 halves, here's 1, 3 halves. If x is negative 1, negative 1 squared is 1, so I get 3 halves also. And I've got this asymptote here, so the curve is going to have a kind of like a bell-shaped look to it, and it's going to be upside down here. Now, what if we wanted to find the limit as x approaches infinity of 3x squared over x squared plus 3? Well, that would be 3, right? As x is heading outward towards infinity, the curve is getting closer and closer to y equal 3. Now, it will never get to y equal 3, but that's where we're headed towards, right? With the limit, it's all about where the y values are approaching. If we wanted to know the limit as x approaches negative infinity of 3x squared over x squared plus 1, that would also be 3, because if I head out towards the negative direction, the y values are also getting closer and closer to 3. Okay, now these two limit calculations would be examples of limits at infinity. Here's a definition. The limit as x approaches infinity of f of x equal L means values of f of x can be made arbitrarily close to L by taking x to be sufficiently large. If the limit as x approaches infinity of f of x equal L, or the limit as x approaches in negative infinity of f of x equal L, then the line y equal L is a horizontal asymptote of the graph of f. Okay, so these two limits were examples of limits at infinity I mentioned. There's a connection with limits at infinity and horizontal asymptotes. Okay. We see that here. Y equal 3 would be a horizontal asymptote, and that is because the value of these two limits were 3. If the value of either one were 3, we would be able to get a horizontal asymptote at y equal 3. Now, a limit at infinity just simply means that x is approaching infinity or x is approaching negative infinity. Now, that is different from an infinite limit. Infinite limits were mentioned in section 2.2, and an infinite limit is where you're looking at the behavior of the y values, and the y values are approaching infinity or negative infinity, not the x values. So with an infinite limit, the value of the limit was either going to be infinity or negative infinity, or does not exist. You know, if you have a vertical asymptote and the curve is shooting off in two different directions there, you'd have a limit that does not exist. Okay, so take note of that. And of course, there's a connection with asymptotes, okay, with limits at infinity, just like there's a connection with asymptotes with infinite limits. Okay, an infinite limit told you where a vertical asymptote was. A limit at infinity is going to tell you where a horizontal asymptote is. Okay. Now, of course, in taking algebra, I mean, you guys are already familiar with the idea of an asymptote, right? But an algebra student is limited in what they can know about graphing functions with asymptotes. Okay, I'll talk more about that later here, but suppose here's an example. Suppose that we want to find the limit as x approaches infinity of tangent inverse of x. Okay, so I've mentioned that the graph of the tangent inverse curve is a graph that you would want to know. That will come up. Okay, here's the graph. And now we have two horizontal asymptotes, one at y equal pi over 2 and one at y equal negative pi over 2. As x is growing without a bound in the positive direction, y is getting closer and closer to pi over 2, okay, because I have that asymptote there. So the value of that limit would therefore be pi over 2. On page 137, problem number 4, I have my book here, flip to that page. Here's problem 4. So they give you a graph, which is actually this graph here, and we're going to answer some questions about the graph, parts A through F. Okay, so the graph of a function g of x is given right here, and in part A, we want to find the limit as x approaches infinity of g of x. So, well, if you head outward towards infinity, the y values are getting closer and closer to 2, and therefore the value of that limit would be 2. Okay, and that's a limit at infinity. Part B would be another limit at infinity. We want to find the limit as x approaches negative infinity of g of x. Well, if I head outward towards the negative direction there, it looks like the y values are getting closer and closer to negative 1, excuse me. And so the value of that limit, therefore, would be negative 1. Okay. Part C, the limit as x approaches 0 of g of x. Well, let's see. If I'm on either side of 0, getting closer and closer to 0, the y values on either side are growing without a bound in the negative direction. So negative infinity would be the value of that limit. Okay. And of course, that limit there in part C would be an example of an infinite limit. Okay. Again, different from a limit at infinity. Part D, we want to find the limit as x approaches 2 from the left of g of x. Okay, so if I'm on the left side of 2, the y values are growing without a bound in the negative direction. Okay, as I get closer to negative 2 there on the left. So negative infinity would be the answer to that one. Again, that would be an example of an infinite limit. Infinite limit, again, just means that your answer is going to be either infinity or negative infinity, or it does not exist. Okay. Part F, part E is what we're on. The limit as x approaches 2 from the right of g of x. Okay, well, that's going to be infinity. So if I'm on the right side of 2, getting closer to 2, the y values are growing without a bound in the positive direction. Infinity would be that answer. Okay, now they're not asking for it, but if we wanted to know the limit as x approaches 2 of g of x, that does not exist, right? Because you're shooting off in different directions there. Part F, state the equations of the asymptotes. Okay, so we're going to have two horizontal asymptotes at y equal 2 and y equal negative 1. By the way, that is because of these limits at infinity that we were calculating in A and B, that we get these two horizontal asymptotes. We're going to have two vertical asymptotes at x equals 0 and x equal 2, and that is because of these infinite limits that we were getting here in part C, D, and E. Okay, now I don't have a formula representing g of x, right? So the whole idea with this problem is to make the connection with a horizontal asymptote and a limit at infinity, as well as a vertical asymptote and an infinite limit. Okay. Next thing is a theorem. Oh, and by the way, when we state the equation of an asymptote, be sure that you're writing it as an equation. Okay, I think I've mentioned that before, but don't just write 0 and 2. Okay, I would take points off for that because that can be confusing. A student could look at this and think, oh, y equals 0 and y equal 2 are the asymptotes. Then no, they're not. X equals 0 and x equal 2, right? So be sure that you write it as an equation, just as they're asking for there in the problem, the equations of the asymptotes. Okay, and that'll be how WebAssign will want the answers typed in also as equations. Okay, let's take a look at, here's the theorem. Let r be some positive number, okay, then the limit as x approaches infinity of 1 over x to the r is 0, and the limit as x approaches negative infinity of 1 over x to the r is 0. Okay, I think this should make total sense to us. So 1 over x to the r is a fraction, and if the denominator is growing without a bound, as the numerator just sits at 1, well then the corresponding output values are going to be getting very small, right? Closer and closer to 0. Same thing if you're approaching negative infinity, okay? Like the denominator is growing without a bound in the negative direction as the numerator just sits at 1. Well, that's going to mean that these fractions here, these negative numbers, are going to be very minuscule then, okay? Getting closer and closer to 0. Now, when we work with limits at infinity, here's an example, we're going to need to use this theorem in the calculation, okay, and that'll be nearly all these calculations. You'll be using this theorem here, so consider that. Okay, so how about let's take a look at this example. Okay, I want to find the limit as x approaches infinity of 4x squared minus x minus 5 over 9x squared plus 2x plus 1. Okay, now the strategy here is to rewrite this function into a form where each of the terms are of the form 1 over x to the r, and then I can use my limit laws and get the answer. Okay, so to begin, I'm going to multiply the top and the bottom by 1 over x squared. 1 over x squared over 1 over x squared is 1, so there's no harm with multiplying this by 1. I'm not changing anything. When you distribute 1 over x squared in the numerator, 4x squared over x squared is 4, and then minus x over x squared, that's minus 1 over x, minus 5 over x squared would be at the end. And then in the denominator, we've got 9x squared over x squared, that's 9, plus 2x over x squared, that's 2 over x, and then plus 1 over x squared is at the end. Okay, now I can use my limit laws. I can split this single limit into 6 different limits. I've done that on the next step. And now limit of a constant is always the constant, right? So you're going to have 4 and then minus. The limit as x approaches infinity of 1 over x, that'd be 0. Since the denominator is growing without a bound, as the numerator just sits at 1, you get 0. Minus 5 times the limit as x approaches infinity of 1 over x squared, that would also be 0. Since the denominator is growing without a bound, as the numerator just sits at 1, you get 0. 5 times 0 is 0. Divided by limit of a constant is always the constant, so you can have 9 plus 2 times the limit as x approaches infinity of 1 over x, that would be 0, plus the limit as x approaches infinity of 1 over x squared, that's 0. Again, the denominator is going to be growing without a bound as the numerator just sits at 1. So these fractions are going to be very minuscule numbers getting closer and closer to 0. 4/9 is the answer. Now, by the way, from what we already know from algebra, notice how in this function the degree at the top is the same as the degree at the bottom. And whenever that happens, you're going to have a horizontal asymptote, but it's not going to be at y equals 0. It's going to be at y equals some other number, okay? And you can easily get that number by comparing the leading coefficients with the highest degree there. So in this problem, like I got a 4 in front of x squared up top, a 9 in front of x squared down under. Y equal 4/9 is a horizontal asymptote. Okay, so 4/9 is going to be the value of this limit at infinity because, again, there's a connection with limits at infinity and horizontal asymptotes. Okay, so in this problem, like I could have already known the answer before I even started any of this here, okay, from what I already know in algebra. Now, a problem like this, I feel, is a very simple problem because you could already know the answer, okay? This isn't a great problem for a calc student, okay, because they already know the answer, all right? Now, algebra students are limited in what they can do with asymptotes, okay? All they know about asymptotes is, in the case of a horizontal asymptote, is compare the degree of the top to the degree of the bottom. Okay, well that's great if you have something in the form polynomial over polynomial, but there are lots of other functions that are going to have asymptotes that have nothing to do with polynomial over polynomial. Okay, so the only way to know what those boundaries are is to know calculus, right? Why don't we stop there?